Hi, all, and welcome to our next lesson on probability. And today we're going to talk about something that we call the fundamental counting principle. So these are all different ways that we can talk about how to group things together or how to find a bunch of combinations of ways for things to happen. So we're going to start off, and for today's lesson, you guys are going to need your calculators, so please make sure that you keep a calculator next to you. And besides for having a calculator, you can print out these notes and follow along with me as we're working on it. So we're going to start off by defining what we call the fundamental counting principle. And the fundamental counting principle helps us to determine the number of ways an event can occur. And it states the following. If we have N of A outcomes in event A, so let's say we have an event occurring, and that event has a bunch of outcomes. Let's say there are 8 different ways to cook an egg. And if we have another event occurring, N of B, if we have an event B occurring, then event B has N of B outcomes. Let's say that event B represents how many ways there are to cook bread. Let's say we have, to toast, to make toast. Let's say we have 3 ways to make toast. Okay, so we have 8 ways to cook eggs and 3 ways to make toast. Then there are N of A times N of B outcomes in event A and B. So what that means is the number of ways there are to cook eggs and to make toast are going to just be the product of the two. And we talked a little bit about this in the unit before when we were looking at this idea of when you hear the word and, right, then that really means that what you're doing is you're multiplying outcomes together. So note that the order in which the experiments are done does not affect the total number of possible outcomes, and that we can repeat. And we're going to talk about what that repetition means in a few minutes. So if we said, how many ways are there for us to cook eggs and make toast? There are 8 ways to cook eggs. There are 3 ways to make toast. 8 times 3 is a total of 24 possibilities of making eggs or cooking toast. So for an example, Katrina plans on wearing 1 necklace, 1 bracelet, and 1 ring. If she owns 6 necklaces, 8 bracelets, and 5 rings, how many different jewelry combinations can she make? Well, again, what that means is we're looking at the number of necklaces and bracelets and rings. Again, when you hear the word and, remember that we're thinking that and is the same thing as saying multiply those events together. So we have 6 times 8 times 5, which gives us 240 ways to make different jewelry combinations. So this is just an example, but let's take a look at an example that's more, this is a little fun example. Let's take a look at an example that's more kind of based on the probability that we've been talking about. So here are some interesting examples, and you guys have seen these in your everyday life. For my bank, I have Bank of America. My bank requires a 6-digit PIN to take money out from the ATM. So let's talk about how many possibilities for PIN codes there are. So the first thing that I'm going to do is a PIN consists of 6 possible digits. So first digit and second digit and third digit and fourth digit and fifth digit and 6th digit. And when we're saying the word and, it has to have all of these digits: first, second, third, and fourth, and fifth, and 6th. So I'm going to write these little lines here just to represent a space. I'm holding on a space for each one of these digits. Now let's talk about how many possibilities or how many possible outcomes there are for that first digit. Well, we can put the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9 in there. Right? So 10 possibilities: 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. 10 possibilities for that first digit. Second digit, same thing, 10 possibilities. Third digit, same thing, 10 possibilities, right? We could put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Same thing for the fourth one, same thing for the fifth one, same thing for the 6th one. So we have a total of, excuse me, 1, 2, 3, 4, 5, 6, a total of 1,000,000 possible pins based on this information. So we have 1,000,000 pins based on this idea that we have a 6-digit pin. And again, you can use any combination of digits that you want. So this could be 1, 2, 3, 4, 5, 6, but don't choose that as a pin. That's the worst pin ever. It could be 0, 0, 0, 0, 0, 0. Same thing. Don't choose that as a pin. That's the worst pin ever. So we have 1,000,000 possibilities for pins based on these constraints or these restrictions. Well, let's take a look at the next example, which says find the probability that someone guesses your pin on their first try. So if somebody is behind you and let's say that they want to try to steal some information from you, what's the probability that they guess your PIN? Well, there's 1,000,000 possible combinations. So our denominator is going to be 1,000,000. And what's the probability that they guess your PIN on their first try? Well, of those 1,000,000 combinations, your PIN represents one correct combination. So that's 1 divided by 1,000,000. And in terms of probability, we have tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. So that's a pretty small probability of that happening. Now, we're going to expand on that idea of PIN in a few minutes, but let's take a look at some other ideas of PINs or passwords. Let's take a look at this next example, which is a computer password for BMCC has 10 characters. Excuse me. The first 2 characters have to be your initials, and the last 8 characters can be uppercase or lowercase, or they can be numbers. How many passwords are possible? Okay, so let's take a look at this one. Now, again, we're dealing with something that has 10 characters. So what I'm going to do is I'm just going to write 10 little spots here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the first 2 characters have to be your initials. Okay, so if this were mine, or if this were yours, if this was anybody's password, my first 2 would be JH. So we only have one possibility for the first 2, right? Same thing of yours. If you just take your first initial and your last name, first initial of your first name and the first initial of your last name, there's only one possibility for the first 2. Now let's take a look at how many possibilities there are for the remaining 8. Well, so the last 8 characters can be uppercase, lowercase, or numbers. So let's count each one of these. In terms of numbers, remember that we have a total of 10 digits, right? So one of those possibilities is that we have a total of 10 digits. Let's take a look at in terms of uppercase or lowercase. Well, remember that the computer knows that uppercase and lowercase letters are different. So capital A, and you guys know this, right? That you have to use some combination of capital letters and lowercase letters in some passcodes, and they're considered to be 2 different things. So in the alphabet, we have a total of 26 letters. So there's 26 uppercase, and they're different from lowercase, so we're gonna have 26 lowercase. So counting those up, 26 plus 26, that gives us 52. And 52 plus 10 gives us 62. So we have 62 possibilities for those next 8 spots. It could be capital letters. We have 26 of them. It could be lowercase letters. We have 26 of them. Or it could be digits. We have 26 of them. And again, remember when we say or means, or is a hint that we're going to add. So 26 plus 26 is 52, and 52 plus 10 is 62. So we have 1 times 1 times 62. And remember, if you guys remember your algebra, this is the same thing as saying 62 to the 8th power. And I just want you to understand how huge of a number this is. You can put 62 and multiply it by itself 8 times, or in my calculator, I'm doing 62 times, 62 to the 8th power times 1, and the 1 from your first 2 initials aren't going to do anything. So this is the same thing as saying, and I'm going to make sure that you understand also how to convert this. This is the same thing as saying 2.18. 340, 1056, and then in my calculator it says times 10 to the 14th. Now, if you remember from algebra, we talked about scientific notation. This 10 to the 14th means I'm going to pick up this decimal and move it 14 places to the right. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have to move it 5 more places to the right. So that means I'm going to tack 5 zeros on there. 218. 3, 4, 0, 1, 0, 5, 6. I'm going to say 5 zeros. 1, 2, 3, 4, 5. And that number is some huge number. Let's see if I know how to pronounce this. Okay, so we have ones, thousands, millions, billions, trillions, 218 trillion passwords based on these possible conditions. That is a ton. I mean, for fun, let's take a look at the next example. Is find the probability a person guesses your passcode on the first try. Well, that's 1 over 218 trillion, which, I mean, this number, I hope you can see that this number is going to be tiny. I'm going to type it into my calculator. 1 divided by 218,340,1056,000,000. And my calculator gives me pretty much a number, it's 4.58 times 10 to the 15th power, which is the same thing as saying point. Let's see, times 10 to the negative 15th power, excuse me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's pretty much a 0% chance that's going to happen. It's a teeny, teeny, tiny number. Okay, so there are some fun examples when we can use the fundamental counting principle, also known as the FCP, in the real world. And in regards to passwords, you can see why the more restrictions that you have, or excuse me, the more things you open up for passwords, the more characters, the more letters, the more numbers, the smaller the probability is that somebody's going to be able to guess your password, period. The more possibilities that you have, the less of a probability is that somebody's going to be able to guess your password. Okay, well, let's take a look at this last example, which says a computer password can use uppercase, lowercase, or numbers, but no character may repeat. If the password has a total of 8 characters, how many passwords can one make in this manner? Well, let's take a look at this one. 8, so 1, 2, 3, 4, 5, 6, 7, 8. So a computer password can use uppercase, lowercase, or numbers, but no character may repeat. If the password has a total of 8 characters, how many passwords can one make in this manner? Well, as we saw from above, uppercase letters, we know already from above that we have a possibility in the English alphabet, right? It also depends on which alphabet you're using. We have 26 characters for uppercase letters. Lowercase, we also have 26. And then for numbers or digits, we have a total of 10 digits, right? 0 through 9. So that's giving us 62. Now, the difference is that this one says that no character may repeat. So what that means is whatever letter, number, uppercase letter, lowercase letter, or number I use here, I can't use in the next one. So if we have 62 possibilities here, whatever one I put here, I can't use in this one. So that means I only have 61 possibilities here. Similarly, whatever one I put here, I can't reuse this one or this one, so that means I have 60 possibilities here. So if I put a capital A and a 2 here, I can't use those for the next one. So instead of having 62 possibilities, I have 60. And same thing, whatever 3 I put here, I can't use here. Whatever 4 I put there, I can't use for this next one, and so on and so forth. And I hope you can see that we're developing a bit of a pattern here, 56 and 55. And that is the same thing as saying, let's see, so 62 times 61 times 60 times 59 times 58 times 57 times 56 times 55. That gives us a total of, now this is what my calculator says, and again, I want to make sure that you guys are able to convert this from scientific notation, and your calculator will go to scientific notation as a default if the number is too big. It can't handle all those spots. 8933 times 10 to the 14th. Okay, and remember what this means. I'm going to pick up the decimal now and move it 14 places to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have to tack on 5 zeros, right, to hit those 14 place values to the right. So the number looks like this: 1, 3, 6, 3, 2, 5, 8, 9, 3, 3 with 5 zeros. 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 1, 2, 3. 1, 2, oops, sorry, just kidding, 1, 2, 3. So here's this guy. So in terms of possibilities, we have ones, we have thousands, we have millions, we have billions, we have trillions, we have 136 trillion possibilities based on that. So we covered the fundamental counting principle with this lecture, and I'm going to come back and finish talking about permutations and combinations, which is an extension, a little bit of an extension of the fundamental counting principle.